happen to the structure. Since our structural assumption is that all these members, it will have very small deflection only. So this length of this column, it will not change. So it will be like this only, it will come. It cannot go below this point, right? At this point, it will go deflection. It will go deflection this way downwards. Since there is no restraint here, this joint, it will move towards my left hand side. So if we see like this, then this is the fixed point. It will be fixed like this, and then it will move like this. It will move like this, and this is the right angle. This is the rigid connection. So here it will be like a rigid connection. It will be coming here, and then this will have the deflection like this. So if I see here, tension is on this side only, it's coming. Okay, so the Benioff diagram, if we see it while drawing the Benioff diagram, it will look like from this point, the load acting at this point, so 0. The moment into distance is 0. If at this point, if we see moment into force into distance, that will be the moment. It will be linearly varying like this. The moment diagram, the bending moment for this beam, and for this point, if we see the force into distance, that is a moment value, that is tension is this side, and then at this point, if we see, this is the same force, same distance, then even along throughout this column, this force into distance is same. So the column will experience a constant moment only. So constant moment will be looking like this. So this will be the bending moment diagram for this column. It's a constant moments, and bending moment for this beam is, it will look like this. It's linearly, it's varying. So whenever the member and load is parallel, because of that force, that member will experience constant moment. But when this member is perpendicular to the force, as long as the distance exceeds from the load point, the moment also linearly varies. So this is the Benioff diagram for this kind of support. Let us see one more point also, one more example. Same support, if same structure. Suppose if we have additional support like here. If we have a roller kind of support here, imagine here we have this kind of support. It's restraining only in this direction. So what would happen? This particular joint, if we say it, it would be deflecting. This is the rigid joint, right? So it would be, it has to maintain its 90-degree position. So it will be like this, it will come. Since the force is pushing the beam down, this will be deflecting like this. Like earlier, it will be deflecting like this. It will be deflecting like this, and then this is, it's like this. Here at this point, it's a fixed, so it has to come like this. Since this joint and this joint has to, it is connected beam, right? So it has to come like this only. So if you see here, tension is coming here, and tension is this side, and tension is this side for this structure when the force is applied like this. So if we draw the bending moment diagram for this one, same, for this beam, this is the force, and the distance goes increasing this way. So the moment will be going like this linearly, it will be varying it. This is the moment diagram, this is the moment line. And at this point for this column, the force into distance is same. So moment will be the same moment value. Whatever this moment is coming, the same moment value it's coming. And this is the tension side is this side. But here, if you see, tension is this way. So since this is pushing, there will be some additional reaction will be coming here, right? So tension will be this side. So moment will be, moment diagram, if you see it, it will look like this. It's a linear line. This is also linear line only, and there is this curve is going. This is one curvature, this is another curvature. There is a point of contraflux at this point. That's why this is moment is 0 at this point. Okay. So if we draw the Benioff diagram for this member, it would be looking like this. This will be like this linear line. This will be like this moment, and from this point to this point there will be a point of counterflexure, because we have seen in the deflection has a double curvature, this one curvature and this one curvature. Okay, these things we can verify it in the STAD modeling also. If you see here, we'll go to the modeling, analytical modeling, geometry. So you'll use the grids. So we have the structure like this. Okay, and what is this length? We can change that length. The unit is inches, it's coming, so we can change the units. Unit that all we can set earlier itself when we make the model. So now let it be the unit we like this itself. Then we will have the model, and then we will see. Then once you apply the geometry, go to the properties and select some section database. We can add some members. For example, we'll put some W shape. We'll put some W, very small beam, W5. And then we will keep the same beam for all the members. So we have kept the same member for all, same cross section for all these members. Then we will go to the materials tab. I think it's getting start pro edition as. So let's open once again. Just open the same model. Yeah. And if you go to the properties, we have not added any property. We will add property. Small beam, add it, and that beam we will assign to view. So it is assigned. If you go to material, it's a steel material. Specifications, it's not required, and supports you will see. Supports are this point we wanted to create. Fixed support, add it, and use this and use cursor to assign. Yeah, fixed support and loading. Loading we will create a new loads. Load case 1 we will create and add it, and in load case 1 we will add the load, nodal load, and z direction, y direction we will keep, say, 1 kip. Add it. So this 1 kip load I want to assign it. It's upward it goes, but I want it downwards, so I will change it to -1. Modify it, close, it's modified. Now in the analysis tab we will add perform analysis, let it perform, and then run the analysis. You will go to run and run analysis. Once analysis is done, it has 0 errors, no 0 warnings, 0 nodes. Let's go to the processing module. Done. Let's see this one. Okay, now let's view this in this view. So let's see this minimum diagram. If you control and scroll the middle bar, you can see this deflection. You see the deflection, how it looks. This is what we understood, right, in the previous explanation. So here it is one single curvature. This is also one single curvature. That's why moment diagram, if you see, it goes like this, and one single curvature. There is no change in the curvature there. That's why it's not crossing. There is no point of contraflexure here. It's a single curvature. Okay, now let's see the moments, and you see the moments. You see the scale wise. You see when you click here and like scroll it and increase the scale, you can see this is the moment increasing linearly, and this constant moment it comes. And the moment value, if you want to see, let us see the moment values. Where is this point, right? This beam, right? This beam, what's the moment value? 1 kPa applied. The distance is 118. So force into distance is 118. At this end, the moment value is 118. Correct. And then if this beam column also, if you see, this is how much, 157, whatever with the length, this is force parallel to this length, so moment should be constant. So constant moment, if you see here, this is the moment 118. That's the constant moment it comes. If you see here, it's a start point and end point, it's the same 118. It comes the moment values because it's a constant moment all along the length. And if you see this member, if the moment will be varying from 0 at node 1 to it's varying until 118. Okay, that's the second node. So it is increasing. So it should be clear from this explanation. The second one, what we did, we put one support, rotor support on this x direction, right? That also we could see. We will go to analytical modeling and we will add some additional supports. The support is one more support, create fixed, but into means it will take given vertical load also. We just want to create fixed, but in release in fx release, no, we are not giving fx release. Fx only we are arresting, and remaining all are we are releasing it. So add the support, and this is the support, and use cursor to assign. It is assigned here. Okay, and then you could see these supports in this way, either this way or this way, it doesn't matter. So it is arresting like this one only. Let's go to the analysis and let's run the analysis for this load condition with this kind of boundary support. Then there is no error and no warnings. Go to the first module. Done. If you see here, see this deflection shape, what we had explained earlier, our understanding is correct only. You see here, this is the 90-degree it has to maintain. This is a single curvature, but this beam it has to maintain in this one, and here it's a fixed, so it will be a curvature. This is one curvature, this is one curvature. There is a change in the curvature, right? It looks like this, it goes like this and like, right? What I mean that, if you see here, this is 90-degree it is maintaining, right? And then this also has to maintain 90-degree, and since this curvature it goes like this is the one curvature, and then this comes like this, so this is the second curvature. So curvature changes at this point. This is the point of contraflexure. Okay, that is when there is a change in the curvature. This is the point of contraflexure. This is the point of contraflexure, right? So it will be two curvatures are there. This is the point of contraflexure, point of contraflexure. This is the radius, radius of this curve and this curve. That's why minimum diagram, if you see it, it comes in one direction here and another direction here. Let's go and see the Benioff diagram. If you see this video diagram. You see this member is constantly, it's moving, constantly increasing, the moment is coming, and at this point if you see this 118 should come, that is here 118, and then here you see this is 58, it's coming, it's reducing, because if you see some force also it will be coming, right? So let's see the reactions. If you see here reaction 1.1, keep this 1.12 keep into this member length. What is that length? Its length is 157.48. Here moment was 118, right? So 1.12 into 157.48, that is the moment, it's the opposite moment, it's increasing, right? This reaction it will this force is causing one moment, this force is causing additional moment, and opposite. So 58.518, that's the balance moment it's coming here. So it's 118.1. This is 157.2. So if you see here 1.81, then this 52 inch, that becomes the point of counterflexion 0. Here you can see almost 0. So the reaction is 1.12. It's coming, I mean shear value, it's not reaction, this is a shear value 1.12. Whatever the reaction is coming here 1.12, that's a shear value, it's coming here. If you see the shear, constant shear, it will be coming like this, constant shear. This shear will be here. For this member, the shear will be the same uniform 1 kip, and for this it will be 1.1 shear diagram. And then if we see here this member opposite direction, right? This is the maximum is 157 minus 118.11. Length of this member is 157.48, and the shear is 1.122. Yes, 1. Shear is 118.11. So this 58.52 value is coming from this value, because at this end we have the moment of 118. At this end, if you want to see the moment, this moment it continuously it will go, but there is this shear force is creating opposite direction moment. That force is 1.122 into this length. So at this edge, if you see 1.122 into 157, that's the length. So moment will be like this. This is linearly increasing, right? And this is this way, right? So